NASA's Voyager 1 probe, the most distant human-made object in the universe, is once again sending usable information back to Earth. It's astonishing to think that a spacecraft launched nearly half a century ago is still active, still exploring, and still transmitting data across the cold, vast reaches of space. Voyager 1 has gone far beyond its initial mission parameters, venturing into interstellar space, a realm that no other human-made object has reached. Imagine a spacecraft built with 1970s technology, older than the cassette player, still communicating across billions of kilometers. It's a stunning testament to human ingenuity and the enduring legacy of a mission that was once considered temporary. The world recently watched in awe as Voyager 1, despite its age and distance, made a new discovery that has sparked widespread excitement and renewed interest in our place in the cosmos. What could lie hidden out there in the infinite reaches of space? What secrets does this lonely traveler continue to uncover, and what does this mean for us on Earth as we look up and wonder whether we're truly alone in the universe? The question of extraterrestrial life has haunted humanity for generations. Could intelligent life exist elsewhere in the universe? Statistically, it seems almost certain. The sheer number of stars, many of which host planetary systems, makes it nearly impossible to believe that Earth is the only cradle of life. The belief that life, perhaps even intelligent civilizations, exists beyond our solar system is not just hopeful thinking, but a scientific probability supported by astronomical data and logic. If intelligent life does exist out there, then Voyager may be humanity's first emissary, silently announcing our presence to the stars. The origins of the Voyager missions can be traced to a rare planetary alignment, an event that occurs only once every 176 years. This configuration provided a unique opportunity for gravity-assisted grand tour of the outer planets Jupiter, Saturn, Uranus, and Neptune. It was Gary Flandreau of NASA's Jet Propulsion Laboratory who realized this opportunity in the late 1960s with a pencil, a keen intellect, and a deep understanding of orbital mechanics. Flandreau charted a course that would let spacecraft use the gravity of each planet to slingshot toward the next, an elegant maneuver that drastically reduced travel time. What would normally take 30 years to reach Neptune could now be done in just 12, but this golden window wouldn't last. NASA had to move quickly to seize the chance. In 1977, just 15 days apart, NASA launched two nearly identical spacecraft, Voyager 1 and Voyager 2. These twin explorers were built to last 5 years, enough to observe Jupiter and Saturn, but fate had other plans as they ventured deeper into space. Their missions were extended, their trajectories altered, and their goals expanded. They shattered every expectation. They not only completed their grand tour but kept going onward, outward into the great unknown. Decades later they remain operational, continuing to send back data daily from the edges of our solar system, further than any spacecraft has ever traveled. In their early years, the Voyager probes gave humanity its first up-close look at the gas giants and their mysterious moons. They revealed a solar system more dynamic and bizarre than we had imagined. Volcanic eruptions on Jupiter's moon Io, vast ice-covered landscapes on Europa and Ganymede, the haunting ring systems of Saturn, and the strange magnetic fields of the outer planets. All of it was captured and transmitted back to Earth in a stream of revolutionary data. Voyager 2 in particular achieved a singular milestone. It is the only spacecraft to have visited both Uranus and Neptune during its flybys in 1986 and 1989 respectively. It recorded storm systems, intricate ring structures, and magnetic fields tilting at odd angles, all phenomena previously unseen. These Discoveries fundamentally altered our understanding of the solar system's diversity and complexity. Today, over 14 billion km from Earth, these spacecraft, no larger than a compact car, continue to defy the odds, often compared to Volkswagen Beetles for their size and design simplicity. The Voyagers carry with them humanity's ambition, curiosity, and hope. What's most extraordinary is that they accomplish all this with primitive onboard systems. Each probe was equipped with just 69 kilobits of memory, less than the storage capacity of a digital wristwatch. Their instruments store data on magnetic tape recorders before transmitting it back to Earth via 12 wide high-gain antennas. The entire process requires a mere 23 watts of power, the same as a dim household light bulb, and yet from that faint signal, scientists extract insights about the structure of the solar system, the interstellar medium, and the boundaries of our sun's influence. Communication, however, grows harder with each passing day. Voyager 2 signals now take over 18 hours to reach Earth every day. It travels 3 to 4 light seconds farther away. Compounding this challenge is the increasing background noise from Earth itself. Radio waves from smartphones, televisions, and satellites interfere with the delicate task of receiving the Voyager's faint transmissions. Still, NASA's Deep Space Network, a global system of powerful radio antennas, continues to catch these whispers from the void, translating them into meaningful data. What the Voyagers send back isn't just numbers, it's a cosmic narrative unfolding in real time. One of the most fascinating regions of space the Voyagers have helped us understand is the helipause, the boundary where the solar wind, a stream of charged particles emitted by the sun, gives way to the interstellar medium. For decades, scientists speculated about what lay beyond this invisible border. They expected that crossing it would produce a marked increase in cosmic rays, high-energy particles that originate from supernovae and other energetic cosmic events. These rays are largely blocked by the sun's magnetic field, so detecting a spike in their presence would signal that a spacecraft had entered interstellar space. Additionally, a noticeable shift in the magnetic field's direction was expected as the sun's influence waned and the galactic magnetic field began to dominate. Voyager 1 crossed the helipause on August 25, 2012, entering uncharted territory. The data it returned, however, confounded expectations. While there was a sharp rise in plasma density confirming that the spacecraft had exited the heliosphere, there was no significant change in the direction of the magnetic field. This puzzled scientists who had long assumed the field would shift distinctly upon leaving the sun's domain. The reality was far more complex, suggesting that the transition into interstellar space may be more gradual or differently structured than once thought. The boundary between our solar system and the galaxy beyond it turned out was not a sharp line but a diffuse, dynamic region still influenced by solar and galactic forces alike. This ambiguity has led to new questions about the nature of space itself. What does it truly mean to be in interstellar space? Is the helipause a fluctuating frontier, subject to solar cycles and cosmic pressures? Voyager 1's unexpected findings forced scientists to revise long-standing theories and developed new models to explain the interaction between our solar system and the galaxy. As Voyager 2 followed its twin across the boundary in November 2018, it too confirmed a rise in plasma density but again reported little change in magnetic orientation. These results point to a more complex heliospheric structure than previously imagined, possibly a layered or filament region shaped by both internal and external forces. Even more astonishing is that the Voyager probes are still heading toward the Oort cloud, a vast spherical shell of icy bodies, surrounding our solar system, though it may take another 300 years to enter the cloud and 30,000 years to pass through it completely. The Voyagers are on that path. Their journey is one of immense patience and persistence, carried by a flicker of power and a memory from a bygone technological era. They carry with them the golden records, photograph discs, encoded with sounds and images, representing the diversity of life and culture on Earth. Should any intelligent civilization encounter these probes, they will receive a cosmic greeting. We are here, we exist, and we reached this far. The Voyager missions are not just about science or space travel. They are a human story. They embody our drive to explore, to understand, to reach beyond what we know. Every signal received is a triumph of engineering, vision, and perseverance. As the Voyagers continue their trek into the unknown, they carry with them the hopes and dreams of an entire species. They remind us that while we may be small in the cosmic scale, we are capable of great feats. They ask the big questions on our behalf. Where does our solar system end? What lies beyond? Are we alone in a universe teeming with possibilities? The Voyager spacecraft remain our eyes and ears at the frontier of knowledge, whispering back to us across the void, reminding us that the quest for understanding is as infinite as space itself. Despite their distance and age, the Voyager probes continue to inspire scientists, engineers, writers, and dreamers across generations. In many ways, their ongoing journey serves as a time capsule of 20th century ambition, an echo of a time when space was the final frontier and exploration was considered not just a scientific endeavor but a moral imperative. Voyager is not simply a mission of instruments and data. It is a symbol. It is proof that we as a species are capable of sending a tiny piece of ourselves to drift eternally through the cosmos, not with conquest in mind but curiosity. Carl Shawn, one of Voyager's most prominent champions, famously persuaded NASA to turn Voyager 1's camera back toward Earth in 1990, just before its imaging system was powered down. What resulted was one of the most iconic photographs ever taken. The pale blue dot in the image. Earth is a mere speck, less than a pixel, suspended in a beam of sunlight, a fragile blue glimmer in the vastness of space. From a distance of over 6 billion kilometers, everything we are, every war and peace, every joy and sorrow, every civilization and culture is reduced to a mode of dust. That single image reframed our place in the universe, not as its center but as a small part of a much grander, largely unexplored whole. Shawn's reflection on the pale blue is often quoted for good reason. He wrote, "Look again at that, that's here. That's home, that's us." His words continue to resonate, especially now in an age where humanity faces existential challenges: climate change, artificial intelligence, nuclear threats. Voyager reminds us that we are all riding together on this pale blue, and that our survival and progress depend on unity, empathy, and a shared vision for the future. Today, NASA engineers work around the clock to keep these ancient spacecraft operational. They invent clever software patches, reroute systems, and repurpose components never designed for long-term use in interstellar space. These adjustments are often carried out with limited resources and constrained communication windows. A single command sent from Earth can take 18 to 22 hours to reach the spacecraft, meaning a round-trip exchange can take nearly 2 days. There's no real-time troubleshooting here. Every decision must be meticulously planned, tested, and executed with a kind of precision typically reserved for surgery or deep-sea rescue operations. Voyager's longevity is a result of both brilliant engineering and relentless problem-solving. In 2020, engineers faced a critical issue. Voyager 2 had entered a protective safe mode and was no longer transmitting scientific data. It took months of careful diagnostics and delicate instructions to return the spacecraft to full functionality. A maneuver performed from across more than 18 billion kilometers when the signal finally returned and new data began to stream in. Cheers erupted at NASA's Jet Propulsion Laboratory for a brief moment. The aging spacecraft reminded humanity that even in its frailty it still had more to offer as time goes on. Though the Voyager's power supply, fueled by radioactive plutonium, continues to dwindle, NASA has begun the process of shutting down non-essential instruments to conserve energy, prioritizing certain data streams while sacrificing others. Eventually, sometime in the 2030s, the spacecraft will fall silent. There will be no dramatic explosion, no loss of signal in a storm, just a gradual fading, a whisper growing quieter until it's gone. But even when their voices are extinguished, the Voyagers themselves will keep going, sailing silently through the galaxy like interstellar driftwood, testaments to a civilization that once looked outward with hope. What makes the Voyager missions particularly poetic is that they may outlast all other signs of humanity long after Earth cities have eroded, after our satellites have fallen from orbit, and perhaps even after humanity itself has evolved or disappeared. The Voyagers will still be out there, carrying messages in a bottle across the stars. The golden records on board include greetings in 55 languages, sounds of Earth waves crashing, birds singing, a baby crying, and music from Bach to Chuck Berry. They include diagrams of DNA, mathematical definitions, and photographs of life on our world. If they are ever intercepted, they could serve as a Rosetta Stone for a future civilization or an alien one trying to understand who we were.